Every night, industrial power stations like this one generate massive amounts of raw electricity, churning out thousands of megawatts to keep modern society running. But getting power out of the station is a serious engineering problem. If you try to push heavy current through miles of standard copper cable, the resistance acts like friction. The wire heats up, and a huge portion of that energy is lost directly to the surrounding air. Yet somehow, we manage to deliver stable, highly controlled energy from those massive turbines all the way to the fragile filament of a single light bulb. We can only do this because a specific piece of technology bridges the vast distance between the generator and your home without melting the transmission wires in between. That technology is the transformer. You've seen these heavy metal boxes in electrical substations acting as vital checkpoints between the power plant and the city. If you cut one of these open, you'll find a bizarre internal contradiction. Inside are two separate coils of wire wrapped closely together, but physically they never touch. The circuit is completely broken, which raises an obvious question. If there's a physical gap between the input wire and the output wire, how does the electricity actually cross over? This silent, invisible jump is what makes the modern national grid possible. When electrical current flows into the primary coil, it generates an invisible magnetic field that expands outward into the surrounding space. As those expanding magnetic waves wash over the neighboring secondary coil, they induce a brand new electrical voltage in that second wire. There is a major efficiency flaw here. Magnetic fields naturally radiate in all directions. Only a tiny fraction of that field actually hits the secondary coil, while the rest of the energy is lost to the open air. To fix this, engineers insert a solid iron core through both coils. Iron is a high permeability material, which means it acts like a sponge for magnetic flux, trapping it inside. By preventing the field from leaking into the air, the core guides nearly 100% of that magnetic energy directly into the secondary coil. The iron core isn't conducting the electricity itself. It is a highly controlled highway for the magnetic energy, effectively eliminating the penalty of the physical distance between the wires. But this highway comes with a strict rule of physics attached. A magnetic field can only induce a voltage in a wire if that field is constantly moving or changing. This is exactly why direct current, or DC, fails in a transformer. DC creates a static, frozen magnetic field. Because it doesn't move, it transfers exactly zero energy across the core. Alternating current, however, constantly reverses its direction. As the current flips back and forth, the magnetic field rapidly expands and collapses in a continuous rhythm. This equation dictates how we manipulate that voltage. The math dictates that the ratio of the voltages is perfectly equal to the ratio of the number of wire loops. If we wind more loops onto the secondary side, it intercepts more of that changing magnetic flux. 3 times the wire loops results in exactly 3 times the voltage output. The transformer doesn't magically create new power. It simply trades current for voltage, relying entirely on the physical geometry of its copper coils. Take this physics back to the macro scale, and you can see the massive engineering required to build these components for national infrastructure. Right at the power station, huge step-up transformers use that exact turns ratio to push the electrical voltage to extreme levels before transmission. By stepping the voltage up, the system forces the current down. With less current pushing through the cables, the resistance drops, which reduces the amount of energy lost to friction and heat. This strategy is what allows us to efficiently transport massive amounts of power across hundreds of miles of rural landscape via high-voltage lines. Finally, before that power enters a neighborhood, step-down transformers reverse the math. They reduce the number of wire loops to drop the voltage back down to a safe, usable level for household appliances. The national grid is a system of magnetic bridges, continuously stepping voltage up and down, ensuring human progress doesn't burn away in the atmosphere.